All right, let's go into the next one. Let me see. This more than likely will be our last section for today. I might just go. That'll be enough. All right, so we're continuing chapter 12 on statistics. So we're rapidly approaching the end. Once we finish chapter 12, that's going to be the end of the new material for the semester. So then once we finish chapter 12, more than likely we'll just use the remaining time to review and practice and try to get as much stuff in order as possible. Again, if you need support or help, you just have to speak up. Either try to connect with a classmate. Again, I don't know if you guys still have a group meet going or not, but I think it's a good idea. And then try to reach out and try to see if anybody's willing to collaborate. And then also I put some information in Populi on how to connect with a free tutoring service. It's 24 hours. All right. So between the tutors, your classmates, and me, between the three of us, you should be able to get those assignments submitted. Okay. So then 12.4 is over the normal distribution. So now we're kind of just looking at how the data is like arranged and like how it's grouped. Is it spread out? Is it all clustered together? We're just saying, exploring concepts like that. All right. So a few objectives here: recognize characteristics of normal distributions. 2, understand the 65, 68, 95, 99.7 rule. Find scores of a specified number of standard deviations from the average. Use the 68, 95, 99.7 rule. Convert a data item to a z-score. Understand percentiles and quartiles. Use and interpret margins of error, and recognize distributions that are not normal. Okay. So the normal distribution, also called the bell curve or Gaussian distribution. Normal distribution is bell-shaped and symmetric about a vertical line through its center. Mean, median, and mode are all equal and located at the center of the distribution. All right. So whenever we have a normal distribution, mean, median, and mode are the same. They're all at the center. And a normal distribution has this bell shape. All right. It's symmetric about that center line. All right. So this is the shape. This is the general shape of a normal distribution. Okay. The shape of the normal distribution depends on the mean and the standard deviation. These three graphs have the same average or the same mean, but different standard deviations. As the standard deviation increases, the distribution becomes more spread out, but retains its symmetric bell shape. Right. So remember, the higher the standard deviation, the more spread out the data is. Right. So even though these three graphs have the same average, they have different standard deviations. So approximately 68% of the data fall within one standard deviation of the average in both directions, right? So we have this image here, right? 68% of the data falls within one standard deviation. 95% of the data falls within two standard deviations in either direction. And 99.7% of the data falls within three standard deviations of the average. Okay. So let me see. Male adult heights in North America are approximately normally distributed with an average of 70 inches and standard deviation of 4 inches. Find the height that is 2 standard deviations above the mean. Okay. So let me see. I feel like I do better when I have like a rough sketch of my bell-shaped curve. Let's see. So we know on the x-axis we have the height in inches, right? So say this is our average at 70 centimeters. Male heights. Okay. And then say we have our bell-shaped curve, something like this. Okay. And then on the slide that we just had on the previous slide, like when we have one standard deviation, let's see, is it at the inflection point? It kind of is, right? So one standard deviation is about here. Let's see, can we match the colors? We could have, but that's okay. 2 standard deviations is about here. And then 3, a little bit further out, is about there. So I probably should extend my graph. And let me move this over some. So these are approximations. About there, right? Something like that. So if we extend this, right, most of it is there. Okay. So this is the what was it? 68, 95, 99.7 rule. So let's see, 68% goes from basically from here to here. So 68% of the data goes from there to there. Kind of running out of space. I'm going to shrink this down a little bit. Okay. And then 95% of the data should go from here to here. Okay. And then this one, 99.7% of the data should go from here to here. Okay. So it looks like we need to calculate one standard deviation. Let me see. Male heights normally distributed with an average. Oh, they gave it. Oh, got lucky because I was like, wait a minute, we needed some more data. They gave us a standard deviation. So in the earlier examples where we calculated the standard deviation, in this example, they gave us a standard deviation, right? Standard deviation symbol is usually like this. It's a sigma, and we might say like a 1 to signify one standard deviation. We might do like a plus or minus or whatever. Now, it says find a height that is 2 standard deviations above the mean. So then if we take our average, I might be mixing this up a little bit. I'll just call it X bar for now. It might be another symbol, but we want to say the average plus 2 standard deviations, right? Like that, right? So then the average is our 70 plus 2 times our standard deviation is 4 inches. So then 2 standard deviations above is going to be, what is that, 78 centimeters, right? Inches. Inches. Right? All we did was we took the average and we added the standard deviation twice to go up by 8 in this case, okay? So the average plus 2 standard deviations. So then use the distribution of male adult heights in the figure to find the percentage of men in North America with heights between 66 and 74. So, okay, right here. 66 is here, 74 is here. That means 68%. To find the percentage of men whose heights are 66 to 74, 68%. So it's really just a matter of reading the chart. This is what we drew by hand, right? But it should be 68%. 68% of males have heights between 66 and 74. Okay. All right, that's fine. So then the Z-score. So the thing with Z-score, like, it's basically just a standardized form of the normal distribution. And in the previous example, we saw a normal distribution where it was showing us information based on heights in centimeters. Well, then there's information. We have these charts that give us more information about the data, but it's standardized. So we have to standardize our normal distribution. So it's pretty much the same information and it's the same stuff. It's just articulated a little bit different, right? So a Z-score describes how many standard deviations a data item in a normal distribution lies above or below the average, right? So in the previous example, we started with the average in the center, and then we did it in terms of standard deviation. Well, then that's the Z-score is the exact same thing, but instead of having like 70 in the center, a Z-score of 0 means you're at the center. And then a Z-score of 1 means you're one standard deviation above the average, right? So Z is synonymous to like, or similar to standard deviation. It's just articulated differently. Okay, so a Z-score describes how many standard deviations a data item in a normal distribution lies above or below the average. The Z-score can be obtained using, it's going to be your X minus X bar, so the item minus the average divided by the standard deviation, right? Data items above the average have a positive Z-score, and data items below the average have negative Z-scores. The Z-score for the average is going to be 0. So X minus X bar over sigma. Okay. So sometimes you might see me refer to this as, because I'm just used to seeing it as X minus X bar over sigma, like this. All right, and that's a Greek letter sigma. It's a lowercase sigma. Sometimes you might see me refer to it like that. There's actually another form, but we're going to go with that one too for now. So the average weight of newborn infants is 7 pounds and the standard deviation is 0.8. So the weight of newborns infants are normally distributed. Find the z-score for a weight of 9 pounds. So, okay, the z-score, right? So we just said that the z-score is going to be, we said x minus x bar over sigma, right? So in this example, the z-score, I'm just going to abbreviate it as 9 pounds. That one should be, the item is x minus x bar, which is what, 7, the average? Yep. So 9 minus 7 divided by the standard deviation is going to be 0.8. Crunch that number. That's 8 over 10. So then it's going to be 2 times 10 over 8. 20 over 8. 10 over 4, 5 over 2. So 2.5. All right, I'm just doing just doing a calculation. Yeah, 2.5, right? And I think we already had it in the chart. So we see a 9-pound infant is 2.5 standard deviations above the average. Okay. All right. So the item minus the average over the standard deviation, we did the same thing. We got the same result. We're actually kind of moving through this. Let's just keep going. Let me not get overconfident. The minute I get cocky and get overconfident, then I get something that's challenging. Energetically, it never fails, all right? So intelligence quotient, IQs on the standard, I guess, Bennett? It's probably Bennett because I don't see any accents or anything. The Stanford Bennett intelligence tests are normally distributed with an average of 100 and a standard deviation of 16. What is the IQ corresponding to a z-score of this? Okay. So I'm a fan of, I usually like to just start with the formula. Again, my z-score is going to be my x minus x bar over my sigma, right? So now, they gave us the z-score. What else did they give us? They gave us our average, so then we want to solve for x, right? So let's plug in what we have. Again, we're solving for x. The average is 100. Our standard deviation is 16. And our corresponding z-score is a negative 1.5. So then we solve for x, multiply both sides by 16, and add 100. We're going to get negative 1.5 times 16 plus 100. Hey, Google, what's negative 1.5 times 16 plus 100? 24.
Minus 1.5 times 16
76
is 76.
All right. I was racing it. I don't know if I mentioned this. I had a professor at Morehouse when I was a student. He did this demonstration. It was applications of like number theory. He was able to like crunch like ridiculous numbers way faster than a calculator. Like we can tell him 478 times 236, and he'll spit out the answer faster than we can type it in the calculator. And like I don't know if I ever showcase you got like an example of that on a more simple level is like the nines. But I need to physically show you my hands, and I don't really feel like coming on the video right now. Yeah, I'd have to showcase. I'll showcase it another time. Let me try to wrap this up. We got 10 slides. We're actually doing pretty good on time, moving a lot faster than I anticipated. 76 is good. So then percentiles. If n% of the items in the distribution are less than a particular data item, we say that the data item is in the nth percentile of the distribution. Okay. And then quartiles divide the data set into 4 equal parts. The 25th percentile is the first quartile. 25% of the data fall below the first quartile. The 50th percentile is the second quartile. And then the 75th percentile is the third quartile. Okay. Not too terrible. But using z-scores in a table, you can find the percentage of data items that are less than any data item in a normal distribution. In a normal distribution, the mean, median, and mode all have a corresponding z-score of 0 and are the 50th percentile. Thus, 50% of the data items are greater than or equal to the average median and the mode. Okay, let's keep going. So statisticians use properties of normal distributions to estimate the probability that a result obtained from a single sample reflects what is truly happening. If n is a sample size, okay, there is a 95% probability that it lies within 1 over the square root of n of the true population statistics. Plus or minus 1 over root n times 100 is called the margin of error. Okay. If n is a sample size, there's a 95% probability that it lies within 1 over the root n, the margin of error. Okay. So on a random sample of 1172 children ages 6 through 14, 17% of the children said getting bossed around is a bad thing about being a kid. Verify the margin of error. What do we say? Plus or minus 1 over the square root of n times 100%. All right, margin of error. I'm going to abbreviate it as margin of error. We said plus or minus, let me clean it up, plus or minus 1 over the square root of n times 100%. Is our margin of error? It looks. So it looks like all we need is n, which is, it looks like it's the 1172. So it looks like our margin of error, we could say plus or minus 1 over the square root of 1172 times 100%. I guess I need to use my calculator. My dog is warming up her vocal cords. Go lay down. Go lay down. We're almost done. Don't be looking at me. We already know what you're getting ready to do. Yes, somebody's here. You don't have to scream. No. Go lay down. Go lay down. You're going the wrong way. Lay down. Somebody just, go lay down. Yeah, yes, lay down. She's just looking at me. We all know somebody's here, and she's like, as long as you're quiet, you can roam. You start singing, it's gonna be trouble. All right. Let's calculate this. 1 over the square root 1172. Okay. Oh, that's not 11. 1172. Okay. Times 100. Let's just say 2.92% plus or minus. So we'll say approximately it's plus or minus, what do you say, 2.9? No. 2.92%. So then, like 14 point something to 19 point something. 14.08. Let me see. 14.08 to 19.92. All right, let's see how do we do. 2 point, yeah, that's what we got. Okay, so I guess we didn't need that other part. Let's get rid of this. Okay, that's fine. So the sample size is 1172, so the margin of error is approximately 3, plus or minus 3%. So write a statement about the percentage of children who feel that getting bossed around is a bad thing about being a kid. Yeah, okay, that's where we used that, the 14.91. So there's a 95% probability that the true population percentage lies between, okay, so those are the numbers that we had, the 14.1% and the 19.9. That's fine. Okay. Oh, and that brings us to the end. I think we got this. Let's see. This graph represents the population distribution of weekly earnings in the United States. There is no upper limit on weekly earnings. The relatively few people with very high weekly income pulls the mean income into a greater value than the median. The most frequent income, the mode, occurs towards the low end of the data item. This is called a skewed distribution because a large number of the data items are piled up at one end or the other with a tail at the other end. This graph is skewed right. Okay. This graph is skewed right. Okay, so that's just talking about skew. That kind of distorts the normal distribution. Okay, so we made it to this point. We still have like another, a good amount of time. Go ahead. Does somebody have a question? You good? Let me see. The main thing is, okay, so again, current grades are available. Hopefully you all had an opportunity to kind of check them for accuracy. It's a good idea to go ahead and do that now. If I haven't responded to an email, the best is just to ask me to stop me now and we can talk about it. We can do breakout rooms if we need to. I can stop the recording as well. So yeah, if you've emailed me and I haven't replied, just, bring it up now and we can talk about it. Otherwise, we just finished what, 12:4, I think it was. So we don't have that much left. I think we have maybe about 3 sections remaining. So I think what I'm going to do is like next week, more than likely, I will just go ahead and try to finish out the new content. And then once we finish the new, we'll probably use our remaining sessions as review and potential extra credit opportunities. Right. So, we'll talk more about that once we finish the new material. And again, if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great weekend, ladies and gentlemen. See you next week. Same time, same place. Take care. Peace.